Welcome to Work, Energy, and Power. This is the unit that completely changes how you solve physics problems. Up until now, you have relied on kinematics and dynamics to track how objects move, but tracking constantly changing forces and accelerations is mathematically exhausting. This unit introduces a far more elegant framework. By treating energy like an absolute accounting system, you can solve complex mechanical problems using just the initial and final states, entirely bypassing the messy accelerations in between. This sits at the very heart of the Cambridge syllabus, forming the crucial bridge between basic forces and advanced topics like electricity and deformation.
We start our accounting with the fundamental mechanism of energy transfer, mechanical work. In physics, energy is simply the capacity to do work. Work done is defined precisely as the product of a force and the displacement in the direction of that force. You will learn how to handle forces acting at awkward angles using trigonometry, and how to extract work values directly from the area under a force displacement graph. This is the mechanism that moves energy from one store to another.
Once energy is transferred into a system, it has to be stored. We classify these accounts into two main types. First is kinetic energy, the energy an object possesses purely by virtue of its motion. You will derive its formula directly from Newton's laws and the equations of motion. Second is potential energy. This is energy stored either by an object's position in a gravitational field or by its physical deformation, like a stretched spring. You will master calculating both, forming the absolute bedrock for almost every mechanics question you will face in Paper 2.
The strict rule governing all these stores is the principle of conservation of energy. This principle dictates that the total energy of a closed system remains perfectly constant. Energy cannot be created or destroyed, only transformed. When an object moves along a curved path, like a swinging pendulum, its acceleration changes constantly. The standard kinematic equations completely fail here. But energy conservation bypasses the path entirely. You will learn to track these transformations and, crucially, account for energy dissipated as thermal energy due to resistive forces like friction. This is the silent workhorse behind the hardest exam questions.
Finally, we look at how fast these transfers happen and how useful they actually are. Power is defined as the rate of work done. You will calculate it using work divided by time, but Cambridge examiners especially love this equation. Power equals driving force multiplied by velocity. You will use this to link dynamics directly to energy. We will also evaluate efficiency, calculating exactly what fraction of your total input energy performs the task you actually want, rather than being wasted as heat. By the end of this unit, you will be completely fluent in the language of energy. You will calculate the mechanical work done by forces. You will track energy as it shifts between kinetic and potential stores. You will apply the conservation of energy to bypass complex mathematics, and you will determine the power and efficiency of real-world systems. This is your ultimate toolkit for mechanics. Let us get started.